Very good. 342. So now you understand there are 2 atoms of aluminum, 3 of sulfur, and 12 of oxygen, right?
Yeah.
Which brings us to the next type of calculation, the ones with having water crystallization. These are the salts which can actually bond to a specific number of water molecules, which stays the same every time they come up with this formula. We call that as a hydrated salt, and different salts have different number of water molecules, which are written very next to the formula of the salt with just a dot in between, like CuSO4.5H2O or Na2CO3.10H2O and MgCl2 with 6 water molecules. Now, working with MR in this case, this dot simply means addition. So calculate the formula of mass for the formula itself, then calculate for water. The water is 18 actually. You simply need to multiply this number with 18. If you remember or memorize the mass for water, this is not going to be a problem. All right.
Yeah.
However, if you need to work them separately, remember this 10 multiplies with 2 of hydrogen, and this 10 then multiplies with oxygen as well. Which means for the calculation like this, CuSO4.5H2O, CuSO4 is calculated, and then 5 multiplied by 18 will give you the answer for this one. All right?
Yeah.
Okay, why don't you go ahead and calculate this one for me? This is magnesium sulfate, MgSO4, and it has 7 water molecules attached to it. Remember, Mg is 32. Sorry, Mg is 24. Sulfur is 32. Oxygen is 16, and hydrogen is 1.
$150.
No, that's not right. Now, this hint is very important. Sometimes we separately calculate the number of hydrogen and oxygen atoms. What we do is that we multiply the 7 with hydrogen atoms, but we take only a single oxygen after, which is a big mistake every time. And make sure we don't do that. So it's 18 into 7, which is equal to 126. Adding MgSO4 to it is definitely not 150.
So MgSO4 is 120, right?
120, very good. So 120 and 126 should be equal to 246. Are you getting the same number?
Well, for the 7H2O, how would you calculate that? Won't it be 14 and then plus 16?
No, actually there are 7 oxygen atoms. That's the mistake, and that's
yeah.
and that's the hint I actually specified over here. This hint tells you this very same thing. That's a big mistake by students. So let me tell you the same thing again. 18 is the mass for water as a whole. So multiply this 7 by 18. Instead of doing them separately, always do them as a whole. the whole water is 18. So 18 into 7, 126. And 120
Yeah.
of MgSO4 and 126 of water added together, 246.
Yeah, I got 246 now.
Okay, Ayan, let me tell you, I can calculate this stuff faster than your calculator in my mind every time. No matter which new compound you can come up with. We can always race. We can have a competition every time. So try going quickly and correctly, all right?
Okay. Yeah.
Which brings us to our next topic, percentage composition. Now, let me just quickly scroll through the page. Let me see if there are, okay. So this percentage composition seems to be a very small topic over here, but I'm going to extend it after we're done with this part of the page so that the question in exams are not confusing enough for you. Okay, so what is percentage? I think you're pretty good with understanding percentage, as percentage of marks in subjects is a very common thing that we do for students. Your obtained marks are usually divided by your total marks of a paper or a subject, and then we multiply it by 100 and we get the answer for percentage. And multiplying by 100 for percentage is such a common step that students remember it by heart. So percentage of a specific element out of a whole compound, it's pretty easy. Take that specific element's mass, no matter how many atoms are present over there, take the whole element's mass, divide it by the MR, and multiply it by 100. For example, if we are working with copper sulfate and we need percentage of copper, the formula would simply by the mass that copper has in the whole compound, and then the MR, which means the mass of the whole compound, and then multiplied by 100. So it's pretty easy. This is 63.5, and just on the previous page, we had this calculated to be 249.5, just in this page, not even the previous one. Actually, no, this is not 249.5. We need to take this 90 out. Actually, that would be 149. No, 159.5, my bad. Okay, so that's 159.5 because I'm not including the water, and multiplied by 100. There you go. You'll get your answer. All right?
Yeah.
Okay. So in the similar way, the percentage composition works. Why don't you get me the percentage composition? Just a second. Percentage composition of O in MgSO4. You recently calculated MgSO4 to be 120. So you already know what MR is. Go ahead, calculate it for me.
So the total is 120.
Yeah, MgS4, the total is 120. MR, or relative molecular mass, is 120.
%53.3%.
So what did you exactly do? Can you read out your calculations for me?
So I did 16 times 4 to find the oxygen, and then
Right.
I divided that by 120 and then times it by 100.
Pretty good. So it's basically 64 over 120 and multiplied by 100. The answer came out to be 53.3%. Is that so?
Yeah. Yeah.
Yeah, 53.333, whatever that was. Okay.
Yeah.
So that's about it. But I'm going to stop sharing over here, and I'm going to share a whiteboard screen so that we can actually go with percentage composition for all of its type in exams. Percentage composition is actually divided into 3 parts. The first part was for elements, which we already did for percentage of oxygen in MgSO4, and you did that correctly, right? Now,
yeah.
For second part, it may come for ions. For example, they ask you to give us the percentage of sulfate ions in MgSO4. So I hope you understand it only leaves the magnesium out. You're supposed to calculate the rest, divide it by 120 and multiply it by 100.
Yeah.
Go ahead. What's your answer?
Let me calculate it.
All right. Remember, in this case, as we're going with an ion, so only magnesium is left out of the whole thing.
Wait, can you repeat that again, please? For the magnesium one, for the ions,
Yeah.
with the ions.
This only includes sulfur and oxygen. So sulfur is 32 plus oxygen is 16 into 4, which makes the whole thing as 96. 16 into 4 is 64. 64 plus 32 is equal to 96. 96 over 120 into 100. Okay.
Yeah. So
this should give you your answer. What do you think the answer is? You have the calculator. Go ahead.
oh, let's see. 80%.
80?
Yeah.
So 80 it is. All right. The third type is for water. This only is true for the substances which have water of crystallization, just like we discussed Mg-SO4.7H2O. So this should only work for water. That means we are supposed to take mass of water as a numerator, whatever number of water molecules are there, divided by mR, multiply it by 100 then. So we have 7 water molecules, so 7 into 18. If you remember, the whole thing was 246. So that is it. So that's 126 over 246 into 100. The answer to that is, go ahead. Is it 48 point something or 49 point something?
It's 51.22%.
51.22%. All right, good. 3 significant figures are good enough. All right.
Yeah.
So you may write it as 51.2%. If you're going with 4, that's good. But anything less than 3 significant figures is not good. So never round it off to 51. Okay.
Yeah. Yeah.
So that's about it. There are 3 kinds of percentage composition questions that we have seen in past papers. This is not given in the book, but that's what I am here for. So you know how to go with elements, you know how to go with ions or a specific part of the formula. This is this part of the formula that they asked for altogether. So whichever part they cut out in form of ions or other portions, don't worry. This is this part of formula which they cut out, the water of crystallization. So it doesn't matter which part of the formula they cut out, a single element or something as a whole, but you're supposed to take that out. Now, if this formula is used over here, this changes the whole thing. Now, you are supposed to go with it like this. 4 into 16 for this part, plus 7 into 16 for this part. Make sense?
Yeah.
Over 246, which was the whole thing, like over here, and multiply that by 100. Now, this one is 64, and this one is 126, right? Which makes the total?
Yeah.
190.
It's 7. Yeah.
Okay, into 100, which is?
Wait, won't it be 176 over 246?
Oh, my bad. This is not 126. I calculated hydrogen in between. So 176 over 246 into 100, and that is?
71.54%.
71.54%. Okay. So I hope now you understand how to cater elements, ions, and water crystallization as a part of percentage composition. Okay?
Yeah.
So let's save a picture. I'll send you this picture later. Let's get back to the book. So now you understand percentage composition. Okay, moving on. Just a second. The mole, just a second. Before mole, yeah, it's a little after in this book. Okay, let's start with moles. Let me get back to the place where mole was. Before I start mole, let me give you a quick concept of mole on a whiteboard page. All right, begin with a new one. Okay, before I start mole, I usually try to tell my students a few examples from daily life or how the whole mole chapter or these two chapters would work for you. Let me tell you, mole is actually a chemist's unit. Why do we need to come up with this unit? That's because we need to cater the entire chemistry lab in many different states. Now, as we have discussed before, in chemistry lab, the substance may be present in the form of solid state, maybe liquid, maybe gas, or maybe in a solution form. And for all of these four quantities, we do not work with the same set of units. Let me explain myself by starting with solids first. Most of the time in daily life or in chemistry lab, for solids, what we use, the quantity we use is mass. We take solids on the basis of mass. Let's not talk about chemistry lab, let's talk about your daily life. When you go out to purchase solids, most of the time, the eatable stuff in solids are purchased on the basis of mass, the common unit for which is grams or kilograms or any other related units to that. For example, if you go out and you're going to buy some grains or you're going to buy any eatable, most of the time the solid eatables are based on mass, and that's how the price is set. Even on the wrappers, on the packets, you would see that how much do they commonly weigh, right?
Yeah.
So a chemist doesn't just have to work with mass. Sometimes they need to work with liquids and gases. It's not just solids that we need to work with. And most of the liquids and gases, as they're fluids in total and they can flow, we work with another quantity, which is volume. Volume is commonly used for liquids and gases both. For example, your liquids, let's talk about your beverages, are usually present in the form of the units of common units of liters and milliliters. For example, the most common beverages on the planet, Coke, Sprite, Fanta, the common names are present in the form of half liter, a liter, 2 liters, 2.5 liters, 5 liters, in different packings like this. I hope you're familiar with that too, right?
Yeah.
So liter is actually equal to decimeter cube. So we are going to use the same scientific form for something we're commonly familiar with. That's how we handle gases. Then comes the solutions. The solutions are commonly handled on the basis of concentration. And concentration, although it has many other units, just like mass or volume, is mostly catered on the basis of mole per decimeter cube units. All right. So in lab, we need to go with concentration. For example, if I talk about the juices you purchase from market, on the wrappers, on the packings, the most common concentration in mole per decimeter cube or percentage of juice is written right on the top of the packet. All right. If you go ahead and buy syrups and medicine syrups, I mean, the concentration is always written on top. No matter which unit they choose, the concentration is always written over there. And last but not least, there are some specific things which we always deal in terms of quantity, in terms of numbers. For example, when you go out to buy bananas, what do? We count them in dozens. A dozen mean 12. So for a few simple things, we always go with quantity. When we're going to go with quantity, we are going to study Avogadro's number as a conversion factor in your book, which is mostly equal to 6.02 into 10 raised to the power 23, which is always equal to, not mostly, always equal to this number of particles. So actually, mole is the secret unit. Sometimes you deal with solids in masses, or liquids or gases in volumes, or solutions in concentration, or simply counting in quantities, in numbers. Mole can be converted or interconverted back into these units. That's why if you need to deal with multiple things at the same time, which by the way is a case in chemistry, because why? We have mostly to deal with chemical equations, and in chemical equations, a reaction can be filled up with many different states. Just like the one we talked about a couple of pages earlier, potassium was reacting with water, it was producing KOH, and it was producing hydrogen. I don't even know whether you remember it or not, but there was a few things written right with that equation. Potassium was present in solid form, water is a liquid, the KOH produced is an aqueous solution, and hydrogen produced is a gas. So actually, in a simple equation or a reaction, you're dealing with all four states of matter. All four state symbols actually, not states of matter exactly. So if you're talking about potassium, you would most probably take potassium in grams. You would take water in decimeter cubes, centimeter cubes, or units similar to those. You would take KOH in these units. So how are you going to handle so many different units in a single chemical equation? Why? Because you'll convert every unit into mole and mole back into these units. That's how we're going to work for it. And that's why we teach moles to students. All right. But before I move further with this chapter, this means I'm going to give you a convertible formula of mass into moles or backwards. So that's going to be our first formula. This is going to be probably our second one. Maybe this is the third one, and this is the fourth one, which means the same quantity moles will have 4 different formulae in this chapter or in the next one in this book. And that's what moles chapter is all about. So you have 4 different formulae to work with inside an equation, which may consist more than one state symbol. Get the point? Yeah. This actually just acts as a mind map of what we are about to do, just to explain what mole is. I haven't defined mole yet. I have told you what we're going to do in these 2 chapters. Okay, so let me save that again, and let's get back to the book. Now, when I explain this mole quantity, and let me tell you, the unit is mole itself, is just the difference that we haven't written E at the end of it. So this is the quantity, these are the units. The first way is to convert masses into moles. How do we come up with this? Now, we need a formula to come up with this, and the formula is written over here. Number of moles is equal to mass in grams and mass of 1 mole of a substance. Mass of 1 mole of a substance seems like a very difficult quantity. Actually, this can be MR or AR. If it's a simple element, take AR. If it's a whole compound, take MR. Instead of this whole thing, this can work easier in a formula. So either you're converting given mass in the question into moles by this form, or you might be rearranging the formula to convert this into this. So either one of these would be given in the question, and you're going to find the other one. Make sense?
Yeah.
For example, let me give you a couple of questions over here. You are given with 100 grams of common table salt that you eat every day, the formula for which is NaCl. You can convert it into moles. How many moles are there, right? By putting this value in over there, calculating its MR, dividing them both, you'll get the number of moles. Simple enough. Go ahead.
Yeah.
And while you are at it, I'm going to write another question in a slightly different form. And that is, what if I have 2.5 moles of NaCl, the same stuff, and I need to know how much mass of NaCl is in that.
Can you tell me the mass number MR of NaCl?
Oh, Na is actually equal to 23 in periodic table and Cl is 35.5. I believe from these values, you can easily calculate the MR yourself.
Yeah.
Now, instead of telling you MRs, I'll keep telling you the values of the periodic table. So by frequently going through these values, you'd slowly tend to remember what oxygen is, what hydrogen is, carbon is. The first 20 elements are the ones which we ask our students to memorize. But don't go ahead and cram it straightforward. By frequent usage, you will automatically remember them by heart.
The first question is 1.709.
Good. 1.709. In order to get the three significant figures, we can even convert it into 1.71. But if you want to be accurate, that's good. 1.709 grams. Remember, the units are very important in exams.
Yeah.
Sorry, 1.909 moles. My bad. This was not the grams question. This was actually the mole question. So MOL. The next one is, however, mass.
$146.25.
146.25. Now, in this one, you might have seen that he needed, and this is grams, you needed to change this formula into this shape, right? In order to calculate the mass, you took the number of moles, which in my question was 2.5, and you multiplied it with MR. MR, by the way, you calculated to be 58.5, right?
Yeah.
Very good. Good. So that's about it. That's as simple as this formula is. This formula becomes complicated as soon as you need to come up with conversions. So let's write the most basic of conversions that you might need in exams. When it comes to mass, 1 metric ton, this might come as part of exams, is actually equal to 1,000 kilograms or 10 raised to power 6 grams or 1 million grams. So 1 kg is equal to 1,000 grams. 1 mg is equal to 10 raised to power minus 3 grams. And 1 microgram, which might not be a question in exams, but you should know just to be on the safe side. So these are the 4 conversions in case of masses. Right? Now, a couple of moments earlier, I gave you a question. The question was that there are 2.5 moles of NaCl, for which you needed to convert it into mass. What if I ask you the mass, but in the unit of kilograms? Now you already have the answer to this question. All you need to do is to convert it into kilograms. So your answer is now going to be
0.14625.
0.146, right? Kilograms.
25, yeah.
Yeah,
Yeah.
3 significant figures are good enough. That's why I'm going to stick with 146.
Yeah.
Right? Good, good. So again, this changes if I give you the mass in a different unit. For example, I ask you that I have 10.62 kgs of sugar. And let me tell you, the formula of sugar we eat every day is C12H22O11 to moles. Converted into moles, what would be your answer?
Carbon is 14, right?
Carbon is 12. Let me write
Oh,
it
yeah,
for
12.
you here. Yeah, carbon is 12, hydrogen is 1, oxygen is 16. But I believe by now you're already familiar with hydrogen and oxygen since we are using them so much. Remember, this formula always asks you to convert everything into grams. So no matter which unit you come across with in the exams, in the questions, you're supposed to convert that into the standard unit, which is grams. Remember, ton, kilogram, milligram are not the standard units. The standard unit in the case of mass, in case of this mole chapter, is grams.
Yeah.
Once you are done calculating MR, let me know what your MR value is.
My MR value is 342 and my answer is 0.03105.
Wait. I think you never converted kilograms into grams. That's why your answer is so small.
Yeah. Yeah.
So actually now you have 3 steps. Even before you apply the formula, you need to calculate the MR and you need to convert the non-standard units of kilograms into the standard unit of grams before you can apply the formula. Then you go ahead and apply the formula to get the correct answer.
Yeah. I got 31.05 now.
381 point something, right?
Now no, I got 1.05.
Okay, sorry, listening issue, but now you have a much bigger answer. Why? Because you converted kilograms into grams and it turned into a value of 10620 grams, which is a huge value to be divided by 342. Thus the answer is so big now, right?
Yeah.
So make sure you have these mass units with you so that if they come up, and they rarely do it, they usually talk about kgs and tons. They hardly come with milligrams or micrograms, but you should know so that you don't have a problem. And remember, if you know these values, they're going to help you in maths, they're going to help you in physics as well. Yeah. Because the quantities are similar for most of them. So there are some questions over here for practice, but I think that's as much as we need to practice. Past paper questions are going to be much better at this. Yeah. Now, Avogadro's constant, for that, I think we should do